All right, so we're going to start talking about a little bit about notation. We're going to start with this idea that I have this f, and this is read f prime of x. That is the derivative as a function, and that's what we're going to do today. But there's also another notation that we really need to talk about, and to do that, I want to go back and look at the idea of what the slope of the secant line is for a second. So the slope of the secant line is the rate of change between those 2 points. So the slope of the secant line you just get from the change of y over the change of x. Now, moving forward, if we're going to go ahead and talk about the slope of the tangent line or the instantaneous velocity, what we're going to do is we are going to call that, we're going to change that notation, and it's going to become dy dx. Now, this idea of dy dx means that it, and it is read, is the derivative of y with respect to x. It does not mean that they are being divided by each other. It means the derivative of y with respect to x. The rate of change, like the slope, the rate of change of y over x, but at an instant. When you're thinking of this limit process, it's really helpful to think about this as h approaches 0. Think about this as the change of x approaches 0, meaning that as you are getting closer and closer to any limit on both sides of x, from the left side and the right side, that difference becomes almost 0. So we're ready to go ahead and start looking at a problem. Let's go ahead and look at f of x is equal to 2 minus x squared. So we are looking for the f prime of x, which is the first derivative of f of x, and that is the limit as h approaches 0 of f of x plus h minus f of x all over h. And if you're thinking to yourself that all of this inside here looks familiar, you are right. That's the difference quotient from back in college algebra. Let's go ahead and find the limit of this function as h approaches 0. Now, remember what we're doing here is we're taking and replacing x plus h and plugging it in for the x value for the first part. So the first part of the difference quotient is r f of x plus h, which leaves us with 2 minus x plus h quantity squared. Then I go through and subtract the second part, which is my original function, f of x, which in this case is just 2 minus x squared. And I divide all of that by h. Now the first thing you want to do is simplify the numerator. So inside here we are left with 2. Expand this by foiling. So you go through and get that as x squared plus 2xh plus h squared. And then you need to subtract both of these, so that's going to be minus 2 plus x squared. And I'm going to go through and change all of these signs. And this is all divided by h. Now what we have is the limit as h approaches 0 of 2 minus x squared minus 2xh minus h squared minus 2 plus x squared. Now something to note, this portion of the minus f of x will always cancel out with the beginning portion of your function. So the 2 minus 2 is 0, and negative x squared and x squared are 0. And this is all divided by h. So now we have the limit as x approaches 0 of negative 2xh minus h squared all over h. At this point, what we do is we take the greatest common factor in the numerator, which is h, and now I have the limit as h approaches 0 of h. I could have taken a negative out there, but it doesn't matter. That's negative 2x minus h all over h. The h's become 1. And now I can go through and use direct substitution and get the fact that all of this is equal to negative 2x. Now, let me minimize all of this because this now becomes our derivative. So I say that f prime of x is equal to negative 2x. The other notation that I could say is that the derivative of y with respect to x is equal to negative 2x. Now we're going to, on the next part, talk about what that actually means. Okay, so our original function was 2 minus x squared, and we found that the first derivative was equal to negative 2x. To understand this a little bit better, let's take a graph and talk about it. So what does all of this mean? All right, so let's say, for example, I want to explore what happens at f of 1. All right, so at f of 1, that just gives me my function at 2 minus 1 squared, or that's just equal to 1. Or f of 1 is equal to 1. That point on that graph is right here. Now, what about the slope of the tangent line at that point? The slope of the, and we'll draw that tangent line in. Now, the slope of the tangent line at that point would be plugging in the same value 1, but this time into the derivative function. So I plug that into negative 2x, and now I'm left with negative 2 times 1, or negative 2, and that does this slope of the tangent line is equal to negative 2. I can extend that and use that for any piece. Let's say I wanted to go ahead and extend this and do it again, but now I wanted to find out that value, the value of the derivative at 0. The value of the function at 0 is 2. But the value of the derivative at 0 is negative 2 times 0, or 0. And this is the slope of the tangent line here. And that is, again, this tangent at this point, it has a slope at 0. So there's a couple things going on here. It's important to understand what the difference is in the language. The function of the derivative is negative 2x, and this will give you the slope at any point. So this is the function of all of the slopes at any particular place. But if you want the actual value of the derivative, you find the function of the derivative first, then plug in the point. We're going to look at the graphs of the derivatives using Desmos.